Welcome to the TrackForce lab. The objective for today's lab is we want to determine how does the shape of an object affects the drag force it experiences. This lab is pretty similar to Wind Tunnel 2 in the fact that we need to measure the pressure from the top to the bottom of the straight duct. However, this time we're going to be using these three rods to measure the pressure in front and behind it. As you can see, we have here this rectangular rod. We also have this cylindrical rod, and we have this semicircular rod with a flat face and a concave face. So the first part of the procedure is to put one of these rods inside the duct, and we need to screw them over here in the middle. And once we do that, we're going to put our pitot tube through this hole over here in the front, all the way to the middle of the duct, so that we can measure the pressure at the entrance of the duct. Once we do that part, we're going to move the pitot tube to exactly 4 inches away from our rod, and we're going to start measuring our pressure from the bottom to the top in increments of 1 centimeter. Once we get out of those pressures, we can convert them to velocity so that we can find our drag force using equation 1 and equation 2 as seen in your procedure manual. Once you get out of that, you guys will continue your analysis to determine which of these shapes experience the most drag force. So that's it for the procedures. Let's go into the lab so that we can get our results. Alright, now that we have finished already using the semicircular rod with the flat face on the front, what we're going to do right now is we're just going to rotate it so that we have the circular face facing forward, and we're going to repeat the process of measuring all the pressures from the top to the bottom. Once we finish with this rod, we're just going to switch to use one of the square or the other cylindrical ones. And once we have gathered all the data for the drag force, we're just going to continue with the analysis part of our lab. So for the analysis part for your drag force lab, we're going to have our 2 equations. So if you see them over there in the procedure manual, we have equation 1 and equation 2. If we see equation 1, you see the equation is 1/2 times the density of the fluid, in this case will be air, times the frontal area of the shape that we're using, the different rods, times the drag coefficient times the velocity square. So let's go over. So as we say, the density is just the density of the air, and the area will be the frontal area. So over here we have different rods, and these are their cross sections. So you can see we have the square rod with a drag coefficient of 2.2, the cylindrical with a 0.3, the semicircular with a concave face on the front is 1.2, and the semicircular with a flat face in front is at 1.7. All of this have the same cross sectional, the same frontal area. So the area you guys will measure just looks something like this. It looks, if you were to see all of these shapes from the front, it just looks like a rectangle of 1 inch by 8 inches. So basically all your frontal areas will be 8 inches square. And then the coefficient of drag is just depending on which of the shapes you're using. The velocity square will be the velocity that we measure in the front when we put the pitot tube in the front. This will be the velocity infinity, or u infinity, or v infinity, depending how you read it in your manual. And once you plug in all those values, you will get your result in either newtons or pounds. So make sure you're working with the consistent units. If you're going to be using the feet per second and the area in inches and so on, make sure you use all of them in imperial units, convert everything to imperial, or make sure you convert everything to SI so you can get either newtons or pounds, because we're measuring force. So just before you do the calculations, make sure everything is consistent for the units. So if you were doing your lab, you can see this was pretty much the setup. We have our duct, we have the shape in the middle, and we have placed our pitot tube 4 inches from the shape. And once you plot out your pressures, you can see we get kind of this shape. It looks kind of like an M or like a V. It looks really different from what we were measuring in other labs when this was our velocity profile. You can see it starts at the very edges. It's kind of low because due to the friction, but as we move away from the edges, it increases a little bit of velocity. But once we're closer to the shape, you can see we get this decrease and then it goes back away. So something you can notice is that the velocity profile changes as you get close to the middle. Most of the shapes will give you this kind of profile. It's just when you have a different figure, you may have slightly different increase or decrease in some of the sections. So you have to make your graph of these shapes in your notebook and in your report of the velocity profile versus the distance and the duct, just like we did with wind tunnel 2. And then we're going to be calculating also the drag force using equation 2 over here. The same equation should use same units. It's just that, well, this one is more like a general equation that takes in consideration only the velocity at the front and the shape of the rod. This one takes in consideration every single one of the increments that you guys were doing. You were doing in increments of 1 centimeter all the way up or down from the duct. So this is what this takes into account, the velocity at each of the single one of the points. So you can see same thing. We have the density of the air times the length, which in this case is the 4 inches that we have the pitot tube away from the shape. And then it's a summation from the first centimeter from the first point to the 20th, meaning from the top to the bottom, bottom to top, times UI, or the velocity at each of the increments. And this UI, we have done it before in wind tunnel 2. You can see this is the formula, but we can simplify it to the 66.65 times the square root of your pressure. So just get the velocity at each of your pressure, at each of the points, just like we have been doing in the previous labs, and that will be your UI. And it will be multiplied times the velocity at the front that we measure when the pitot tube was at the front, minus the velocity at whichever point in Y you're measuring, multiply times your distance or your height in Y. So once again, is the density of the air times the length times the summation, everything is adding up, of the velocity at each point times the difference between the velocity at the entrance minus the velocity at any point, multiply times the height that you're testing that pressure at. So once you plug in all of this, make sure you have your units consistent. As you can see, the UI is also in feet per second. So just make sure you work with imperial units all throughout, feet per second, pounds, etc., inches, feet, or just change everything to SI so you can have a consistent and end up with newtons. So make sure you do this for all the shapes. So you will do both the equation 1 and 2 for each one of the shapes, and you will plot the velocity profile for all the graphs. So you basically will end up a graph with all the velocity profiles of all the shapes, and you will also do the mathematical calculations with equation 1 and 2 to see which of these produces the highest amount of drag force. And what we mean by drag force is just the force that's opposite, that's giving you resistance to move in a fluid. If we were to plot to show that graphically, we can have one force, this is thrust, that is moving over here, and the opposite reaction force will be your drag, that is caused by the fluid resistance, for example, air resistance or something. So that's pretty much what drag is, just the resistance or the opposite force when you're moving through a fluid. Something I want you guys to notice for the analysis part is this little pocket of air that's formed exactly behind the shape that experiences the drag. Something to put it in practical terms is, have you seen how all the cyclists in the Tour de France, they're lining up behind each other? What that does is that it reduces the drag that the cyclists experience behind the leader. So the leader will act as this shape. That person will experience all the drag. So it will make this pocket of air so that all the people behind the cyclist, behind the leader, if they fall in this part, they won't be experiencing as much drag as they would if they were either more far away or if they were on the sides. So by everyone making a line in exactly this pocket right after the other, all of the people behind it don't experience as much resistance from the air, so they get less tired and they can continue to cycle longer distances that involve in the Tour de France. Another example is also the birds. You see how most of the birds, they fly like in a V shape. Same thing, the leader is absorbing all the drag while everyone else gets their resistance reduced. Another example is when you're driving behind an 18-wheeler. Sometimes we have heard that driving too close to an 18-wheeler is really dangerous, because if you fall on their blind spot and they brake or something, you might get into an accident. But another reason is that when you're driving behind the 18-wheeler, you can see it forms the same shape, it forms the same pocket of air, so that you don't experience as much of the air force or the drags to your car. So when you drive at a certain distance, you might fall on this pocket, so your car won't experience as much drag, and it will save you some gas and mileage if you fall yourself in this part, your car will not waste as much gas since there's not really much resistance it's facing from the upcoming wind. And this is the side view. If we look at the top view, however, we can see that this shape is still present, and you can see how if you're exactly behind it at a certain distance, as we said, you will not experience as much drag. But once you move away to either to the left or to the right, all the gusts of wind that comes from the sides of the 18-wheeler will be enough to probably push you away. So that's why when you're driving too close to 18-wheelers and they pass you and you pass them, you have to be really careful to not get hit by one of these gusts of wind that will move you, shake you, and maybe cause of an accident in the highway. So be really careful when you're doing that. But as you can see, drag is something we experience in everyday things in everyday life, when driving, when cycling, when walking, even in the pool, when swimming. So just pay attention to the shapy forms. As I said, with different shapes produce different rods, different objects produce different patterns, but the principle is the same no matter what. So now you can take advantage of this and you can use it for any application you guys want.